My name is Alex Klotz. I'm a professor at Cal State Long Beach, and I'm talking about some work I did with a student, Matthew Maldonado, looking at some properties of tight knots. This is a recording of the presentation I gave at the 2023 APS March Meeting in Las Vegas. So I got into this field as a postdoc, doing experiments with knotted DNA molecules. And it's been known for about 20 years that the simplest knot tied in DNA will have a contour length of about 200 nanometers. The knots I was looking at had microns or tens of microns of DNA, so they were orders of magnitude bigger and likely orders of magnitude more topologically complex, but we couldn't actually resolve the topology due to diffraction limits. So I began to wonder whether it was possible to constrain the topology of these knots based on their apparent size. And this brought me into contact with something from math called the rope length problem, which basically asks if you have an inextensible, incompressible rope and you tie a knot in it, what is the minimum length needed to tie that knot? Or if you have a rope that's an inch thick and a foot long, can you tie a knot in it? More generally, we can ask if a knot has some minimum number C of crossings, what are the upper and lower bound of the rope length as a function of C? There's a few things known about this. It's known that for any family of knots, the rope length will scale as a power of the crossing number, where that power is between 3/4 and 1. There are upper and lower bounds that any knot must satisfy. And computationally, we can measure upper bounds, which get pretty tight. For example, this is the tightest trefoil knot, and it has a rope length of less than 32 3/4. People have computed rope lengths for every knot with up to 11 crossings, as well as topological links. You can see the distribution here on the left, where it splits into alternating and non-alternating knots. If you plot this on a on a log-log graph, it falls on a power law, and that power is is about 0.81, so between that 3/4 and 1 limit. And I think there's still a few things that we can ask and then answer about this. For example, we can ask, is there a crossing rope length scaling exponent for the ensemble of all knots? Is there a reason it appears close to 0.81? If we measure bigger and bigger knots, will that number hold? There are conjectural bounds that are stronger than proven bounds for the rope length crossing relationship. But these are not very well constrained by existing measurements, so we can perhaps tighten these conjectural bounds. And these proven rope length limits apply as the crossing number tends towards infinity. They can measure up to 11, which is not close to infinity. So how complex does a knot have to be before these asymptotic scaling limits start to apply? To answer questions like this, we use clever geometry and an algorithm called constrained gradient optimization, which is implemented in a software called RidgeRunner, developed by Jason Cantarella, which basically takes a discrete knot and perturbs its points and follows the gradient towards smaller contour length. And I implemented this on an Amazon web server and trained a student, Matthew Maldonado, how to use it. So the first thing we investigated was what's called a satellite knot. So if you take an elastic band, tie it in a knot, and then cut the loop outside the knot and glue it back together in a non-trivial way, you get a satellite knot. I was interested in these, one, because I spent a lot of time playing with elastic bands, and two, because if you look at a diagram of one of these knots, you see every crossing becomes 4 crossings. If this increases the rope length by a set amount, call that X, then we know that the rope length crossing scaling exponent will be log X over log 4. So Matthew basically measured every satellite of every knot with up to 8 crossings for 3 different kinds of satellites. This extended sort of the measurement limits from 11 up to 34. And generally speaking, he found that the rope length approximately triples when it's tied into a satellite. So this means there's this rope length scaling crossing exponent of log 3 over log 4, or about 0.79. This is close to that 0.81 that was known for already measured knots. Does this necessarily apply to every knot besides the specific set of satellite knots? Obviously, that's too strong a claim to make, but I think this is intriguing. So doing this made us realize that computation is slow, and I really wanted to push this limit of measured rope lengths beyond 11, beyond 34. And to do that, I needed a type of knot with the most crossings for the fewest vertices. And that type of knot is what I call a symmetric torus knot, where the rope wraps around a bagel p times in one direction and p plus times in the other direction, having a crossing number of then p squared minus 1. So the trefoil is an example, but this here is a 26-25 torus knot, which has 624 crossings. We showed it had a rope length of less than 1396. So we measured the rope lengths of these torus knots from 3 crossings up to 1023. So we've gone up 2 orders of magnitude. And the data in green lies on a power law. So we can do a fit and find that it's 0.71. That is below the 3/4 limit, which is mathematically proven. So did I discover something mathematically impossible? Not exactly, but it requires explanation. So we can understand sort of these tight entanglements in general by imagining n links that are each wrapped or are entangled with n other links by Hopf linking. When these are tightened, I don't know what their configuration will be, but I do know that every loop has to wrap around every other loop. And that means it cannot be shorter than the smallest path around n identical disks. This is known as the minimal convex hull problem. In the large n limit, this becomes hexagonal close packing surrounded by a circle. But for intermediate n, the loop is not generally known, but is known not to be a circle or even symmetric. So if we take data from this sort of numerical data from this optimization problem and apply it to derive an expression for the rope length, where the number of disks is approximately the square root of the number of crossings, we can have a relationship that relies on this 2D optimization data. So here's the data from our rope length computations, and here are the results of that minimal convex hull model. I generated the data before I came up with this model. I saw this, I'm sure you can imagine I was pleasantly surprised. So going back to my motivating questions, can we find an exponent for the ensemble of all knots? Not yet, we can't, but I think this satellite 0.79 thing is intriguing. I didn't talk about it too much, but we sort of increased and decreased the prefactors on a few sort of upper and lower bounds. And what I think is most interesting is that we know for a knot to be asymptotically complex, the square root of its crossing number has to have, as a collection of disks, has to have a convex hull that is approximately circular. And this is not reached even when the crossing number approaches 1,000. So very big. Now that's what I want to say about length. I'll also tell you a bit about volume. So it's known that as a knot shrinks, it eventually undergoes a buckling transition. This knot, its torus knot, is initially in a plane, and as it shrinks, it buckles out of that plane, which you can see happening in these animations. This can perhaps increase the overall volume of the knot as defined by its convex hull, even as the length decreases. So that led me to wonder, does the tightest knot have the smallest volume? And if you've seen the title of my paper, you know that the answer is no. The tightest knot is not necessarily the smallest. Well, the counterexample I found was the 819 knot, which has a tightest configuration, which is bigger than a looser one. I'm sure there's more out there, but I only needed to find one. So there's always more knots to shrink. If you're watching this and want to try it out, I can help you get that set up. I think as a scientist, it's important to remember the motivation and not just shrink a big knot for its own sake and pose well-motivated problems. So currently, I have a student, Caleb Anderson, looking at twisted polycatenanes like we see in this animation, and that's motivated by DNA supercoiling, and hopefully we'll get to talk about it in the future. Thank you.